Hello, and welcome to this presentation titled Kruskal-Based Approximation Algorithm for the Multi-Level Steiner Tree Problem. My name is Richard Spence, and this will be a joint presentation with Rayan Ahmed. We are both PhD candidates at the University of Arizona in Tucson. So let's first review the Steiner tree problem in graphs. So if we're given an undirected graph G and a subset T of vertices, which we call terminals, we say that a Steiner tree of G over T is a subtree that spans these terminals. So the Steiner tree is not required to include vertices which are not terminals. So this is one main distinction between this problem and, say, the minimum spanning tree problem. So some basic facts about the Steiner tree problem in graphs. So it is NP-hard. However, it does admit constant approximation algorithms. So the currently best known approximation is with ratio approximately 1.39 by Burka et al. On the other hand, it is hard to approximate this problem arbitrarily close to 1. So in this paper, we study a generalization of the Steiner tree problem where the terminal vertices require different priority level or quality of service requirements. So we call this problem the multi-level Steiner tree problem. However, it does have other names in literature, including multi-level network design from some papers in the 90s, quality of service multicast tree, priority Steiner tree, multi-tier tree, and so on. So the idea behind this problem is that we're given a graph with terminals, such as the example on the left. So in the example on the left, we have a graph with 9 terminals. 5 of these terminals require a higher priority, indicated by the larger circles, and 4 of them require less priority. So for this problem, we want to compute a Steiner tree such that higher priority terminals are connected using higher quality edges. So in this example solution, we have the 5 terminals, say with priority 2. They are connected using edges with a higher rate or a higher cost. So we'll formally define this problem in the next slide. The drawing on the right shows an equivalent multi-level visualization of this example solution with the input graph on the bottom. So let's define the problem a little bit more formally. So as before, we're given a graph. It's undirected, as well as a set of terminals where each terminal requires some priority between 1 and L. We use L for the highest priority or level and 1 for the lowest. So we say that a multi-level Steiner tree is a tree G prime containing edges of different rates, also between 1 and L, such that for any 2 terminals, U and V in the terminal set, the path connecting them in the tree uses edges whose rate is greater than or equal to the minimum of the priorities of the 2 endpoints. So as example, we see in this picture that we have priority 2 terminals which are connected using rate 2 edges, and any pair of terminals is connected using edges with rate at least 1. So how do we define the cost of a solution? So we'll define a cost for each edge at each rate, which we denote by C sub I of E. And we'll simply define the cost of a solution to be the sum of all the edge costs in the tree at their respective rates. And as a special case of this, we say that edge costs are proportional if the cost of including an edge is proportional to its rate. So if the cost of including an edge with rate I is equal to I times the cost of including that same edge with rate 1. So this problem is to find a minimum cost multi-level Steiner tree given a graph with terminals and priorities. This does generalize the Steiner tree problem, so it is NP hard, which means that we'll want to try to find approximation algorithms that approximate the minimum cost MLST. So there are some known results on this problem. In the special case where the costs are proportional, there are constant approximation algorithms. With more general unrestricted edge costs, there is a O of log t approximation by Charikar et al., which we'll go over shortly. On the other hand, this is hard to approximate with ratio c times log n for some constant c under some complexity assumptions. So this was a 2008 paper by Chuzoy et al. So in this paper, we consider generalizations of Kruskal's and Prim's algorithms for the minimum spanning tree problem. And we show how to extend these to the multi-level Steiner tree problem. We show that a suitable Kruskal-based approach gives a 2 LNT approximation. And this matches the best known approximation by Charikar et al. On the other hand, a Prim-based generalization gets a bit trickier. If you just try to generalize Prim's algorithm, it can perform arbitrarily poorly with respect to the optimum. And lastly, we provide experimental comparison between our proposed logarithmic approximation versus the one by Charikar et al. And we compare the quality of the solutions returned with respect to the number of vertices, the number of levels or priorities, using different graph generators. So first, let's review the 2 LNT approximation by Charikar et al. The idea behind this algorithm is fairly simple. It's a greedy algorithm. So this algorithm considers the terminals by order of priority, starting with the highest priority terminals, and simply connects each terminal to the existing tree using the cheapest possible path, taking into account the costs at each rate. So starting with the highest priority terminal, or sometimes called the root, it simply connects each terminal to the existing MLST. So this is a 2 LNT plus 1 approximation, which we'll just say roughly 2 log t. So the algorithm that we proposed is somewhat different, but the analysis behaves very similarly. The idea is that instead of connecting the terminals by priority, as in Charikar et al., we're instead going to connect the cheapest pair of terminals at each iteration. So what do you mean by this? So instead of connecting terminals by priority, we're just going to find the pair of terminals in the terminal set that minimizes their connection cost, and then connect them using edges of the appropriate rate. So once we do that, we remove the lower priority terminal from the set of terminals and continue this process until all the terminals are connected to form a subgraph, which we can then prune away cycles to enforce that the subgraph is a tree. So it can be shown similarly that this is also a 2 times the natural log of t approximation, independent of L, or the number of priorities. So in the next portion, Rayan is going to go over the integer linear programming formulations for this problem, as well as experimental results.